Hello, my name is Pablo. I am a master's student at University of Tennessee at Chattanooga, and I work with the Connected Smart research group in this institution. Today I'll be presenting about our research on distributed inter-area oscillation damping control via dynamic average consensus. This is an overview of our presentation today. Our motivation for this work is to address the integration of inverter-based renewable energy resources on the power grid. And as we know, frequency excursions they happen in a transmission system when you have sudden changes or large changes on power. As renewable generation is inherently intermittent, it's reasonable to assume that a transmission system with high penetration of those resources will be more stressed. And therefore, in the future, generators they will need new control laws in order to keep synchronism between each other. In this work, we address specifically what we call inter-area oscillation. This figure illustrates the 11 bus 2 area from Kunduz. Initially, the system is in steady state, and there's a power flow between area 1 and area 2 of 413 megawatts. At time O equals 1, there's a change in 5% of the voltage reference in machine 1, which lasts for 12 cycles. On this next figure, you can see that as the disturbance happens, the frequency of each generation bus changes from its nominal value, and not only changes, but area 1 generators, they oscillate against the ones in area 2. That's what's called inter-area oscillation. Of course, this is an extreme case. We removed the PSS in the simulation just for the sake of illustrating the outcomes of this problem. In this next slide, you see a scheme showing us an example of how diverse a transmission system can be. So it has traditional energy sources such as thermal power plants, hydropower, and then you have inverter-based energy resources as wind generation and solar power plant. As you mentioned previously, those resources they are intermittent. And for sudden variations in power, you have sudden variations in frequency, and those usually are addressed by those controllable energy resources. Therefore, synchronous generators they need new control laws in order to maintain synchronism in a very intermittent power grid. Before we dive into the proposed control, I want to explain some concepts. Dynamic average consensus, I will explain the swing equation, and modal analysis. In this figure, you have a communication network. This is a graph representing the line connections of IEEE 39 bus case. Because our control relies on the average frequency of the grid, then we have to come up with some algorithm that can calculate in a distributed fashion what the average frequency is. That's when the average consensus comes into play. Supposing each agent in this network has given value x and you want to obtain the average of x on the whole grid among all the agents. In a centralized fashion, what you do is we basically sum all the z values and divide it by the number of agents. However, in a distributed fashion, when each agent only has access to its direct neighbor values, such averaging process can be accomplished by using the average consensus technique. The mathematical formulation of the static average consensus consists of a double stochastic matrix W, which is based on the network graph, and a vector x containing the local values of x for each agent. The vector x is iteratively updated as it is multiplied by the matrix W. After many iterations, each element in X will carry the average value of the initial vector. The more connected the communication graph is, the faster the average consensus will reach to the final average. Conversely, the more sparse the communication network is, the slower it will be the convergence process, and therefore the simulation will need more iterations to converge. In our simulations, the value x being broadcasted to other agents is called gamma, and it stands for the average frequency of the grid. In the case when the values of x are changing for each agent, there is a need to include the update bias to the values that are being broadcasted. We call this variable z, which is a bias term that will allow the algorithm to converge to the average even with these changes on time. Another important mathematical background for this research is the swing equation, which is described by this formula. Basically, what it tells us is how much the frequency changes for any change in power. After a given disturbance, the inertia will provide the power, which will slow down the rotating machine, that will lead to a drop in frequency. This drop in frequency will cause some loads to consume less power since they are frequency dependent, such as motors, for instance. This behavior is captured by this element d times omega s, which is the damping factor. Now we will expand the swing equation for all generation buses on the network, and for that you use the subscript I to denote these buses. If you linearize these equations on the operating point and you rewrite them in a vector format, then you can obtain the following equations, which you use later for modal analysis of our control. This is the matrix representation of such a system, and the A matrix represents the linearized form of the equations we just mentioned in the previous slide. And the eigenvalues of this matrix will dictate the stability of the network. If the eigenvalues are on the left-hand side of the imaginary plane, then we have stable modes. Otherwise, if the eigenvalues lie on the right-hand side, then you have unstable modes, which we are trying to eliminate here. It's important to add that the further to the left the eigenvalues are, the faster the oscillatory modes will dump before the system reaches a steady state. The distributed frequency deviation control is the proposed solution to mitigate inter-area oscillation in this work. The block diagram illustrates the idea behind its operation. The yellow rectangles represent buses, which are modeled based on the swing equation shown on the blue line. There is a communication block that represents the connection network linking all the agents. In this network, each agent broadcasts to its neighbors their perception of the average frequency of the grid. In other words, their value of gamma. In red, you see the block diagram of the DFDC. Locally, each agent receives its neighbor values of gamma, and after they are locally averaged and updated by the bias value, the local gamma is then subtracted from the local frequency perceived on the bus. Afterwards, this difference in frequency is multiplied by the gain k, that equals to the amount of power to be injected or absorbed from the grid by the storage device being operated by the control. This diagram shows how we consider the power flow in these equations and illustrates where this energy storage system should be added on the generation buses and in the load buses in order to enable damping control. In this figure, we show the equations related to each part of the block diagram, together with the final format of the equation we will be using from now on. Now, gamma is the only element on our equationing that is still missing an equation for us to build the state space model. So in this slide, I'll show you how we can calculate it using the dynamic average consensus. This equation expresses the standard formulation for the dynamic average consensus that you showed previously in the preliminaries. And our goal now is to use this equation to calculate the average frequency on the grid. In order to translate this equation to a continuous time, we are adding each end of the equation minus gamma to the k, and you are dividing each element by delta t, which is a small variation time. Then finally you can obtain a continuous time equation for gamma. In order to simplify the equationing, let's create a new variable called beta, where beta equals omega minus gamma. If you develop this equation, then we can obtain the following values for the derivative of beta. Finally, we obtain the following state equations that represent the linearized form of the power grid with the DFDC control. This state space model will be used to perform modal analysis and to perform the time domain simulations. The simulation setup you choose to perform in this study was two bus systems, IEEE 57 bus and IEEE 118 bus. Both of them are shown in this figure. The communication network existent between the generation buses is equivalent to the transmission line connection graphs. We are also assuming that all the generation buses will have the same value of K, and the disturbances they happen on the load side. In this section, we will show the model analysis results for IEEE 57 and 118 bus case. The model analysis was performed by calculating the eigenvalues of the state matrix A with the proposed control for various values of K, varying from 0 to 10. As you can see in the figure, the eigenvalues move towards the left-hand side as the gain K increases, which indicates that the system becomes more stable as the oscillatory modes damp faster when higher values of K are achieved. It is also possible to see in the figure D that some eigenvalues that related to the lumped system and related to the angle tilde, they remain the same for any value of K, which indicates that there's no changing inertia or damping in the system. Similar results were obtained for 118 bus case, as you can see in this figure. This bar diagram illustrates the percentage of eigenvalues that have its damping coefficient within a specific range for a given gain K. Let's take for instance the figure A, which shows the results for IEEE 57 bus case. In the original case, when K equals to 0, about 62% of the eigenvalues are poorly damped. As you can see in the blue bar, most eigenvalues damping lies below 10%. A similar result is also observed in figure B, which illustrates the results for IEEE 118 bus case. However, as we increase the gain K to 10, more eigenvalue starts to present higher damping. And the same can be observed as we increase the gain K afterwards. Another point we observed is that one-third of the eigenvalues, which corresponds to the beta state, remain with higher damping. That suggests to us that the averaging processes converges to steady state faster in this network. These are the results for the time domain simulation. On the first row, you can see the results for 57 bus. On the first figure, we have the applying disturbances. On the second figure, you have what would be the system response in the original case without any control. On the third figure, we have the response for the lumped system. Supposing we have all the inertia, all the damping, everything in just one bus. How would the frequency behave? It's just one unique curve describing the frequency. On the last figure, we have the system response that corresponds to a system that has the proposed control. If you compare the frequency response with the lumped system, you see quite similar profile because all the frequencies they're traveling together very close from what would be the response in the lumped system. And that shows us that there's very few inter-area oscillation between the generators contained in the transmission network. So in this work, an inter-area oscillation damping control is proposed. It's based on the difference between the frequencies of individual buses and the average frequency. It can easily be accomplished by the dynamic average consensus. The proposed control was tested and the 57 bus and the 118 bus in both for time domain and modal analysis. All the oscillatory modes, eigenvalues, they're pushed to the left as we show, which shows a more stable behavior of the power system. And finally, the time domain results, they look very similar to the lumped system, which is the ideal result for such disturbances that we applied on the power system. For future work, we plan to study the impact of communication delays and failures on the control algorithm. We want to study the optimal values of K and the ideal combination of distributed frequency deviation control and PSS, which is power system stabilizer. Another study we want to do is to determine which distributed energy resources would be more appropriate to provide power to the distributed frequency control that you proposed in this work. Thank you so much for your attention. I am looking forward to hear comments and questions and suggestions about our work. Thank you so much. Goodbye.